Pick up a teaspoon. Not a special one. Any teaspoon. The kind sitting in your kitchen drawer right now, unremarkable, used for stirring coffee or measuring sugar or scooping something small out of a jar. Hold it in your hand for a moment. It weighs almost nothing. A few grams at most. Light enough that you could hold 100 of them in one hand without effort. Light enough that a child could carry one. Light enough that you could forget it was there entirely. Now imagine filling that teaspoon with something. Not water, not sand, not any substance you have ever encountered or could encounter on this planet. Imagine filling it with the densest material in the observable universe. Material so compressed, so unimaginably dense, that the laws of physics governing it are different from the laws that govern everything else you have ever touched or seen or known. Imagine filling that teaspoon with the interior of a neutron star. That teaspoon in your hand would now weigh approximately 1 billion tons. Not a million, not 100 million, 1 billion tons. The weight of every mountain range on Earth combined, compressed into a volume smaller than a sugar cube, sitting in an ordinary kitchen utensil. And that is not even the most extraordinary thing about a neutron star. That is just the beginning. We are going to follow this object, the neutron star, from its beginning to its present. From the moment it was born in the most violent event the universe produces, through the physics of what it is and how it works, to the edge of what it tells us about the nature of matter itself and the limits of what can exist. By the end, the teaspoon in your kitchen will mean something different than it did before. To understand what a neutron star is, we have to understand what a star is. Not in the loose, familiar sense, a bright point in the night sky, a source of warmth and light, but in the precise, physical sense. What is actually happening inside a star? And why does it matter for what comes after? A star is a negotiation. On one side of that negotiation is gravity. Every bit of mass in the universe attracts every other bit of mass. For an object as massive as a star, our Sun contains 99.8% of all the mass in the solar system. The gravitational force pressing inward toward the center is almost incomprehensible. If gravity were the only force at work, a star would collapse instantly into something far smaller and far denser than it currently is. But gravity is not the only force at work. At the center of a star, the pressure and temperature created by that inward gravitational squeeze reach a threshold, approximately 10 million degrees Celsius for a star like our Sun, at which atomic nuclei can overcome their electromagnetic repulsion and fuse together. Hydrogen nuclei fuse into helium, releasing energy in the process. That energy radiates outward, creating a pressure that pushes back against the inward pull of gravity. This balance between the inward crush of gravity and the outward push of fusion energy is what defines a star during most of its life. Physicists call it hydrostatic equilibrium. It is, in a sense, a controlled standoff. Gravity trying to collapse the star, fusion energy trying to blow it apart, the two forces locked in a balance that can last for billions of years. But the balance is not permanent. Stars burn through their fuel. Hydrogen becomes helium. In massive stars, those with more than roughly 8 times the mass of our Sun, the fusion process continues past helium, building heavier and heavier elements in the core. Helium fuses into carbon, carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron, and iron is where the negotiation ends. Iron is the most stable atomic nucleus. It sits at the bottom of the nuclear binding energy curve. It cannot release energy by fusing into something heavier, and it cannot release energy by splitting into something lighter. Iron is nuclear ash. It accumulates in the core of a massive star like sediment, inert and growing. When the iron core grows large enough, when it reaches approximately 1.4 times the mass of our Sun, a threshold known as the Chandrasekhar limit, something catastrophic happens. The negotiation collapses. Gravity wins. What happens next occurs in less than a second. Less than 1 second. For a star that has existed for millions of years, maintaining its balance through continuous nuclear fusion, the end comes in a fraction of a second. The iron core, no longer supported by fusion energy, begins to collapse under its own gravity. The outer layers of the core fall inward at speeds approaching 1/4 of the speed of light. The temperature spikes to hundreds of billions of degrees. The density increases so rapidly that the physics governing the collapse transitions from one regime to another in fractions of a millisecond. At ordinary densities, matter is mostly empty space. You have heard this before. The atom is mostly void, with a tiny nucleus surrounded by a vast electron cloud. If you could remove all the empty space from every atom in your body, what remained would fit in a volume smaller than a grain of sand. As the core collapses, that empty space is removed. The electrons, which normally occupy the vast outer regions of atoms, are forced by the extreme pressure into the atomic nuclei themselves. They combine with protons through a process called electron capture, converting them into neutrons and releasing neutrinos. The atomic structure of matter, the arrangement of nucleus and electron cloud that defines ordinary chemistry and ordinary physics, ceases to exist. What is left is a ball of neutrons, packed together, touching, as densely as neutrons can physically be packed without crossing into something even stranger. This process, the collapse of an iron core into a ball of neutrons, takes approximately 1/4 of a second. The newly formed neutron star is roughly 20 kilometers in diameter. To put that in perspective, our Sun is approximately 1.4 million kilometers in diameter. The core of a massive star, which before the collapse contained more mass than our entire Sun, has been compressed into a sphere smaller than a city. The density of this object is approximately 10 to the power of 17 kilograms per cubic meter. That number is difficult to visualize, so let us approach it differently. The density of water is 1,000 kilograms per cubic meter. The density of iron, one of the densest common materials on Earth, is approximately 7,874 kilograms per cubic meter. The density of a white dwarf, the remnant of a smaller star's death, is approximately 10 to the power of 9 kilograms per cubic meter. Already extraordinary by ordinary standards. The density of a neutron star is 100 million times greater than that. A neutron star is so dense that a single cubic centimeter of its material, a cube roughly the size of a sugar cube, would weigh approximately 100 million tons on Earth. And a teaspoon holds roughly 5 cubic centimeters, hence the billion tons. But we have gotten ahead of ourselves because the birth of a neutron star is not a quiet event. It is the most energetic explosion in the observable universe, short of the Big Bang itself. When the collapsing core bounces, when the neutrons are packed so tightly that the strong nuclear force creates an outward pressure that halts the collapse, the infalling outer layers of the star slam into this newly rigid surface and rebound outward in a shockwave. A supernova. The energy released in a core collapse supernova is extraordinary to the point of being almost impossible to communicate. In the first 10 seconds of the explosion, the energy released is greater than the total energy our Sun will emit over its entire 10 billion-year lifetime. The luminosity of a supernova at its peak can equal the combined light output of an entire galaxy of hundreds of billions of stars. And yet, and this is one of the most startling facts in all of astrophysics, approximately 99% of that energy is not released as light or as the kinetic energy of the explosion. It is released as neutrinos. The electron capture process that creates the neutrons generates an enormous flux of neutrinos, particles so weakly interacting that they pass through ordinary matter almost entirely unaffected. In the core of the collapsing star, even neutrinos are briefly trapped by the extreme density, but they escape within seconds, carrying with them 99% of the explosion's energy. In 1987, a supernova occurred in the Large Magellanic Cloud, a small galaxy approximately 168,000 light-years from Earth. It was the closest observable supernova in nearly 4 centuries, close enough that it was briefly visible to the naked eye in the southern hemisphere. Before the light from the explosion reached Earth, the neutrinos arrived, traveling at nearly the speed of light, passing through 168,000 light-years of space and then through the entire Earth as if it were not there. They were detected by neutrino observatories in Japan, the United States, and the Soviet Union. 24 neutrinos. Out of the 10 to the power of 58 neutrinos produced in the explosion, 24 were caught by instruments designed to detect them. Those 24 neutrinos confirmed the theory of core collapse supernovae that physicists had developed over decades. They confirmed that a neutron star had been born in that explosion. And what was left, at the center of the expanding supernova remnant, was the neutron star itself. Small, dense, hot, and spinning. When a massive star collapses into a neutron star, something happens to its rotation. Stars rotate. Our Sun rotates roughly once every 25 days at its equator. Massive stars rotate faster. Some complete a full rotation in a matter of hours. This rotation is a property of the angular momentum of the gas cloud from which the star formed, and angular momentum is conserved. It cannot be created or destroyed, only transferred. When the core of a massive star, which might be thousands of kilometers across, collapses into a neutron star roughly 20 kilometers in diameter, the angular momentum of that core is conserved in the much smaller object. The effect is the same as what happens when a spinning ice skater pulls in their arms. The rotation accelerates dramatically. A stellar core that was rotating once every few hours becomes a neutron star rotating dozens, hundreds, or even thousands of times per second. Thousands of times per second. These rapidly rotating neutron stars are called pulsars because many of them emit beams of electromagnetic radiation from their magnetic poles, and as they spin, those beams sweep across space like a lighthouse beam sweeping across an ocean. If Earth happens to lie in the path of one of those beams, we detect a pulse of radio waves with each rotation, regular, precise, extraordinarily consistent. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish at Cambridge University. The signal was so regular, pulsars arriving every 1.3373 seconds, with a precision that rivaled the best atomic clocks on Earth, that for a brief period the researchers genuinely considered the possibility that it might be an artificial signal. They labeled the source LGM1, Little Green Men. It was not little green men, it was a neutron star rotating 0.748 times per second, its beam sweeping past Earth with metronomic precision. Since then, thousands of pulsars have been discovered. The fastest known pulsar, PSR, J1748-2446 AD, rotates 716 times per second. Its equator is moving at approximately 24% of the speed of light. An object more massive than our Sun, 20 kilometers across, rotating 716 times per second. The surface of that object is moving at roughly 70,000 kilometers per second. This is a real thing that exists in our galaxy right now. What would the surface of a neutron star be like? This is a question we can approach through physics, even though no human instrument has ever been close to one, and none ever will be. The surface of a neutron star is one of the most extreme environments in the universe, and every aspect of it defies ordinary intuition. The gravity at the surface of a neutron star is approximately 200 billion times stronger than the gravity at Earth's surface. To understand what this means practically, if you dropped an object from a height of 1 meter above the surface of a neutron star, it would hit the surface in about 1 microsecond, traveling at approximately 2,000 kilometers per second at the moment of impact. Nothing survives contact with the surface of a neutron star. Not rock, not metal, not any material that exists on Earth. The gravitational forces would overwhelm every molecular and atomic bond that holds matter together. Anything that approached close enough would be stretched and compressed simultaneously, a process physicists call spaghettification, and then crushed into the surface with a force that converts its structure entirely into the neutron degenerate matter of the star itself. The surface itself, to the extent that a neutron star can be said to have a surface, is thought to consist of a crystalline lattice of atomic nuclei, primarily iron nuclei, embedded in a sea of electrons. This outer crust is perhaps a kilometer thick. Beneath it, the density increases to the point where atomic nuclei dissolve entirely, and the matter becomes a fluid of neutrons. The temperature of a newly formed neutron star is approximately 100 billion degrees Celsius. Over time, millions of years, it cools, radiating energy as X-rays and eventually as visible light. But even an old neutron star maintains a surface temperature of approximately 1 million degrees. Hot enough that its thermal radiation is primarily in the X-ray spectrum, invisible to human eyes, but detectable by space-based X-ray observatories. The magnetic field of a neutron star is equally extreme. Earth's magnetic field has a strength of approximately 25 to 65 microtesla at the surface. The magnetic field of a typical neutron star is approximately 100 million Tesla. The most extreme neutron stars, a subclass called magnetars, have magnetic fields of 100 billion Tesla or more. At those field strengths, the magnetic force is strong enough to distort the electron clouds of atoms, stretching them into thin cylinders aligned with the field lines. The chemistry of matter, the way atoms interact with each other, is fundamentally altered. The periodic table, as we know it, does not apply. The surface of a neutron star is extreme. The interior is where physics reaches its limits. As you descend from the crust into the interior of a neutron star, the density increases steadily. The neutron fluid of the outer core transitions, at greater depths, into regimes where the density exceeds anything achievable in a laboratory on Earth, or indeed anywhere else in the observable universe, except inside neutron stars and black holes. What happens to matter at these densities is one of the most important unsolved problems in theoretical physics. We know that at nuclear density, the density of an atomic nucleus, matter consists of neutrons and protons bound together by the strong nuclear force. But neutron star interiors exceed nuclear density significantly. At these densities, the individual identity of neutrons may dissolve. The quarks that make up neutrons, the fundamental constituents of matter, may become free, no longer confined within individual particles, but existing as a collective fluid. This hypothetical state is called quark matter, or strange matter if it includes strange quarks. It has never been observed directly. It may not exist. But theoretical models of neutron star interiors suggest that the cores of the most massive neutron stars may contain it. There is a further possibility that sits at the very edge of current theoretical understanding. If the core of a neutron star is compressed beyond a certain threshold, if enough mass accumulates, or if two neutron stars merge, the neutron star may collapse further. The neutron degeneracy pressure that holds it up against gravity may be overwhelmed, just as electron degeneracy pressure was overwhelmed when the original stellar core collapsed. And if that happens, there is nothing left to stop the collapse. The neutron star becomes a black hole. This transition from neutron star to black hole is one of the few events in the universe that may occur without any external sign. A neutron star, rotating and pulsing, simply stops pulsing. The signal disappears. Where there was something, there is now a region of space-time from which nothing, not even light, can escape. The most extreme object in the universe, consumed by something more extreme still. Within the population of neutron stars, there exists a subclass so extreme that it deserves its own chapter. Magnetars. A magnetar is a neutron star with a magnetic field so powerful that it represents a qualitatively different kind of object from ordinary neutron stars, not just more extreme on the same scale, but different in the phenomena it produces and the physics it embodies. The magnetic field of a magnetar, reaching 100 billion Tesla or more, stores an enormous amount of energy. When this field shifts or cracks the star's crust, it releases that energy in an instant as a burst of gamma rays and X-rays. On December 27, 2004, a magnetar designated SGR 1806-20 released a burst of energy in approximately a tenth of a second. The energy released in that tenth of a second was greater than the energy our Sun will emit over the next 100,000 years. This burst traveled 50,000 light-years across the galaxy before reaching Earth. By the time it arrived, it had dispersed across the enormous distance and weakened significantly. And yet it was still powerful enough to measurably ionize Earth's upper atmosphere, the ionosphere, and to briefly disrupt radio communications. A cosmic event 50,000 light-years away, releasing its energy in a tenth of a second, affected our planet's atmosphere. Had this magnetar been within a few light-years of Earth, the distance to our nearest stellar neighbor, the burst would have been sufficient to strip away Earth's atmosphere and sterilize the surface entirely. There are no magnetars near Earth, but there are magnetars in our galaxy. There have always been magnetars in our galaxy, and the galaxy is not static. Stars move, Systems change over geological timescales. This is not a threat that requires immediate concern, but it is a reminder of something important. The universe contains objects so extreme that their ordinary day-to-day existence, their resting state, not their catastrophic events, would be immediately fatal to any life within a certain range. Magnetars do not have to do anything extraordinary to be dangerous. They simply have to exist and rotate and be close enough. Let us step back from the extremity for a moment and consider something quieter. Pulsars are, among other things, the most precise natural clocks in the universe. The rotation of a pulsar slows down over time as it loses energy through radiation. But this slowdown is extraordinarily gradual and extraordinarily consistent. By measuring the arrival times of pulsar pulses with sufficient precision, astronomers can track the rotation of a neutron star to a level of accuracy that rivals the best atomic clocks ever built. Some pulsars are so stable that irregularities in their timing can be used to detect things that would otherwise be invisible. In 1974, Russell Hulse and Joseph Taylor discovered a pulsar in a binary system, a neutron star orbiting another neutron star, both of them spinning and emitting pulses. By tracking the arrival times of the pulses from the first neutron star with extraordinary precision over years, they were able to measure the orbital decay of the system. The two neutron stars were spiraling toward each other, losing energy. And the rate at which they were losing energy matched precisely the prediction of general relativity for energy radiated as gravitational waves. This was the first indirect evidence for the existence of gravitational waves, ripples in space-time itself, predicted by Einstein in 1916, but not directly detected until 2015. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery, made entirely through the careful timing of pulsar pulses. Pulsar timing arrays, networks of telescopes monitoring dozens of pulsars simultaneously, are now being used as a galaxy-scale gravitational wave detector. Gravitational waves passing through the galaxy create tiny, correlated delays in the arrival times of pulses from multiple pulsars simultaneously. By monitoring enough pulsars with sufficient precision, astronomers hope to detect gravitational waves from sources too large and too slow for instruments like LIGO to detect, merging supermassive black holes, the gravitational background of the early universe. A neutron star, born in violence, spinning with incomprehensible speed, is being used as an instrument of extraordinary delicacy to probe the structure of space-time itself. On August 17, 2017, something happened that physicists had predicted but never observed. Two neutron stars, orbiting each other in a binary system approximately 130 million light-years away, completed their long in-spiral and merged. The gravitational waves from this merger, designated GW170817, were detected by the LIGO and Virgo gravitational wave observatories. For the first time in history, a gravitational wave signal had been detected from a known astronomical source. Within seconds, the alert went out to observatories around the world. What followed was the most coordinated astronomical observation in history. Telescopes on every continent, in space and on the ground, across the electromagnetic spectrum from radio waves to gamma rays, turned toward the source of the signal. They saw a kilonova. When two neutron stars merge, the collision produces conditions of extraordinary temperature and density. In these conditions, rapid neutron capture, the R process, occurs. Heavy elements, heavier than iron, are synthesized in enormous quantities. Gold, platinum, uranium. The heaviest elements in the periodic table, created in the violent collision of two of the densest objects in the universe. The kilonova from GW 170817 produced, in a fraction of a second, an estimated quantity of gold equivalent to several times the mass of Earth. All the gold that has ever been mined on Earth, all the gold in every vault, every piece of jewelry, every electronic device. It was made in events like this one. In the collision of neutron stars, in the most violent mergers the universe produces outside of black hole formation. The gold in a wedding ring was forged in the collision of two neutron stars, somewhere in the universe, at some point in the past, before the solar system existed. And we watched it happen, in real time, on August 17th, 2017. For the first time in the history of our species, a neutron star is not simply an extreme object to be catalogued alongside other extreme objects. It is a laboratory. The only laboratory in the universe where certain kinds of physics can be studied, because the conditions required to produce those physics cannot be replicated anywhere else. The interior of a neutron star reaches densities that no particle accelerator on Earth has ever achieved or will achieve in the foreseeable future. The physics of matter at those densities, the behavior of quarks, the nature of the strong nuclear force at extreme compression, the possible existence of exotic states of matter, can only be studied by observing neutron stars and comparing the observations with theoretical predictions. The equation of state of neutron star matter, the relationship between its pressure, density, and temperature, is one of the most important unsolved problems in nuclear physics. Different theoretical models predict different equations of state, and those differences produce different observable properties. A neutron star described by one equation of state will have a slightly different radius, a slightly different maximum mass, a slightly different response to tidal forces in a binary system than one described by another equation of state. The gravitational wave observation of GW 170817 provided the first measurement of neutron star tidal deformability, a measure of how much a neutron star is distorted by the gravity of its companion during the inspiral. This measurement constrained the equation of state more tightly than any previous observation. Future gravitational wave detections of neutron star mergers will constrain it further. The next generation of gravitational wave detectors, Einstein Telescope, Cosmic Explorer, will detect neutron star mergers at distances of billions of light years, accumulating a statistical sample that will eventually determine the equation of state of neutron star matter with precision. We are, in other words, using the most extreme objects in the universe to do fundamental physics, using gravity to probe matter, using the deaths of stars to understand the behavior of quarks. This is what science looks like at its most ambitious, not a controlled experiment in a laboratory, but the patient observation of a universe that runs its own experiments on scales and at energies we could never produce ourselves. Come back to the teaspoon. You understand it differently now, not just the number, 1 billion tons, but what that number represents, what it took to produce material that dense, what it means for matter to exist in that state. The material in a neutron star was once part of a massive star, burning through its nuclear fuel over millions of years, building heavy elements in its core layer by layer, until the iron accumulated and the negotiation between gravity and fusion energy collapsed in less than a second. The matter that is now neutron degenerate, packed so tightly that individual atoms no longer exist, that electrons have been forced into protons, that the very concept of chemistry is meaningless, was once the interior of a star, was once interstellar gas, was once part of the debris of an even earlier stellar generation. The density of a neutron star is not just an extreme number, it is the result of a process, a history, a journey through stellar birth and death and collapse that took millions of years and ended in a quarter of a second. And a teaspoon of it would weigh 1 billion tons, not because of some arbitrary property of the material, but because of what matter becomes when gravity has compressed it beyond every threshold it can normally maintain. When the empty space in atoms is gone, when the atoms themselves are gone, when all that remains is the densest stable arrangement of the matter that the laws of physics permit. The kitchen drawer that holds your teaspoon also holds, in some sense, a connection to all of this. Not directly, the atoms in your teaspoon are not from a neutron star, but the processes that made those atoms, the stellar nucleosynthesis, the supernova explosions, are the same processes that produced neutron stars. The same physics, the same events, different outcomes depending on the mass of the star that died and the conditions of its collapse. Your teaspoon and a neutron star are products of the same universe, governed by the same laws, made of matter that has been through similar journeys. The difference between them is a matter of degree, of how far the compression went, of what the gravity was strong enough to do. There is a final question that a neutron star raises. Not about neutron stars specifically, but about matter itself. What are the limits? We have followed matter through several transitions, from ordinary atoms with their vast empty spaces and their electron clouds and their chemistry, to the degenerate electron gas of a white dwarf, where electrons are packed so tightly they can go no further, to the neutron degenerate matter of a neutron star, where electrons no longer exist as electrons and neutrons are packed to nuclear density. Each transition is a response to gravity, overwhelming a form of pressure that previously resisted it. Electron degeneracy pressure fails and is replaced by neutron degeneracy pressure. Neutron degeneracy pressure, in turn, has its own limit. Above approximately 2 to 3 times the mass of our Sun, the exact number depends on the equation of state, which we do not yet fully know, neutron degeneracy pressure fails. There is no known form of pressure that can resist gravity beyond this point. The collapse continues, and the result is a black hole, a region of space-time where the curvature is so extreme that not even light can escape, where the concept of a surface, of a material with properties that can be measured, ceases to apply in any ordinary sense. A neutron star is, in this sense, the last stand of matter. The densest thing that can exist while still being a thing, while still having a surface, a temperature, a magnetic field, a rotation rate, a composition. Beyond it lies something that is no longer matter in any conventional sense, but a property of space-time itself. The neutron star sits at the boundary. On one side, matter, strange, extreme, barely recognizable matter, but matter nonetheless. On the other side, something for which the word matter no longer applies. It is the edge of what can exist as stuff. Step outside tonight and look at the stars. What you are looking at is not a static backdrop. It is a population of objects in various stages of their lives. Some of those stars are young, still converting hydrogen to helium in their cores, billions of years from their end. Some are old, exhausting their fuel, beginning the transitions that will lead to their deaths. Some have already died, their light still traveling toward us, the death itself already complete. And some of those deaths have already produced neutron stars. Right now, in our galaxy alone, there are estimated to be approximately 1 billion neutron stars. 1 billion objects, each more massive than our Sun, each compressed into a sphere 20 kilometers across, each spinning, many of them pulsing, some of them radiating X-rays, a few of them generating magnetic fields strong enough to alter the chemistry of matter itself. 1 billion of them. In our galaxy alone, in a universe of hundreds of billions of galaxies. The universe is not a quiet place, even when it appears quiet. Beneath the stillness of the stars, extreme physics is operating continuously, collapses occurring, supernovae igniting, neutron stars spinning down over millions of years, binary systems spiraling toward mergers that will forge the heavy elements and send gravitational waves rippling across space-time. All of it governed by the same laws that govern the teaspoon in your kitchen drawer. The same gravity, the same nuclear forces, the same fundamental physics, just operating at scales and densities so far from ordinary experience that the results seem impossible. They are not impossible. They are the universe, doing what the universe does, at the extremes of what its own laws permit. The teaspoon in your hand weighs a few grams. Fill it with the interior of a neutron star, and it would weigh 1 billion tons. Both of those facts are true. Both of them describe the same universe. And the distance between them, the gulf, between a few grams and 1 billion tons, between an ordinary kitchen utensil and the densest object in existence, is a measure of how much the universe contains that we have not yet fully understood, and how much further there is still to go.